Hello class, Mr. Buford, I'm back. We're going to be looking at quadratic functions, and in this case we're going to be looking at quadratic functions. This is our new topic, quadratic functions, where we're factoring for the case where a is greater than 1. But in this case, a is greater than 1 only because we have a factor in our quadratic function that can actually be factored out of the function. And once we factor it out of the function, then the quadratic function is pretty much like the quadratic functions that you solved before when a equals 1. And so that's the big idea here, is the method that you used to factor quadratic functions when a is equal 1. We are pretty much going to use that same method here, because for these equations we will be able to factor out something called the greatest common factor, which is basically a number. We'll be able to pull that number out of the quadratic function, so that after we pull that number out, the a coefficient in the quadratic function becomes 1 again, and then you can go ahead and factor the equation just like you factored it in the previous assignment. The only thing that you have to remember to do is when you come up with your two binomial expressions that represent the product of the two binomials, you have to multiply those two expressions by the greatest common factor that you pulled out of the equation. So I'm going to go through two examples that show you this, and that should be sufficient to get you started on working on the problems that we have for you this week. So let's go ahead and get started. As you see here, we've got some general rules. It says in general, when a is greater than 1 before factoring the greatest common factor, a is equal to 1 after factoring the greatest common factor. So again, what that's just saying is that before we factored out this number, the a coefficient of our quadratic function is greater than 1. But once we factor out that greatest common factor, the a coefficient becomes 1, and we can therefore factor the quadratic function the way that we factored it in previous assignments. Okay? And so the greatest common factor is that number that we sort of pull out of the quadratic function, so that our quadratic function basically looks like it looked before, where a was equal to 1. So let's look at an example of this. Our first example, we have a quadratic function that's equal to 6x squared plus 30x plus 36. And so what we can do using the distributive process is to pull a 6 out of each of these terms. As you can see, each of these terms, the 6x squared term, the 30x term, and the 36 term, each of those can be divided by 6. So we can pull 6 out of this equation, and when we do that, you see we have this quadratic function here. So if we pull 6 out of this term, we'd be left with 6, which is what we have here. If we pulled 6 out of this term, we'd have 5 left, which is what we have here. And if we pulled 6 out of this term, we'd only have x squared left. which is what we have here. So when we say we're pulling 6 out, 6 is our greatest common factor because it's the largest number that we can pull out of the equation. When we do that, it's the largest number that we can pull from all terms. And when we do that, our equation looks like this. So here's our greatest common factor, 6. The remaining quadratic function is x squared plus 5x plus 6. And we know how to factor that type of an equation. So we go back to the method that we used before. The only difference here is that we have that greatest common factor multiplied on the outside of the equation. And again, since it's multiplied, since we've pulled it out, and it has to be multiplied times the original quadratic function, when we take this x squared plus 5x plus 6 and make it into two binomial expressions, we still have to multiply those two binomial expressions by this 6 here. So that's the only difference. So to find the factors of this quadratic function that's inside here, we do it the way that we did before. In order to find g and h, remember g and h, the sum of g and h have to equal b, and b is 5, and the product of g and h have to equal c, which is 6. So from here, what we could do is we could go to the quadratic function worksheet and find out the g and h that allows us to have those numbers. But if we remember our times table, we know that the numbers 2 times 3 would give us 6, and also if you add 2 and 3 together, they will give us 5. So therefore, since 2 and 3 satisfies both of these criteria, where 2 times 3 equals 6 and 2 plus 3 equals 5, then g and h must equal 2 and h must equal 3. And therefore we can substitute the 2 value here, the 3 value here, and then that will satisfy our equation. And so that's what we do here. We say that 6 times x squared plus 5x plus 6 must be equal to 6 times x plus 2 times x plus 3. And so again, this process is almost identical to the process that we used to solve for quadratic functions when a is equal to 1. All we've done is we've pulled out the greatest common factor, which is 6. Now we have a quadratic function where a is equal to 1 again. We solve for this quadratic function under the criteria that we use when a is equal to 1, and that's how we get our solution. So let's look at another example. Here we have a much larger number, 648, and again a is greater than 1. So let's see if we can find a greatest common factor that we can pull out of this number. Another way of thinking about pulling it out is if we divide each term by 6, by a minus 3. Here we divided each term by 6. You see, in effect, if we divide each of these terms by 6, we get this quadratic function here, and then we pull that out here. So if we want to pull 3 out of here, it's just like dividing each of these terms by 3. And in this case, it would be like dividing them by a negative 3. And so when we do that, the greatest common factor is minus 3, and when we divide each of these terms by a minus 3, you see what we have left is minus 216, minus 19, and a 1 in front of x squared. So again, basically we have a quadratic function with a equals to 1, so we can use the methods that we've used before. The only thing we have to do is multiply the resulting two binomial expressions by the greatest common factor, which in this case is minus 3. So again, what we do is we're looking for a g and h such that the product of g and h gives us minus 216, and the sum of g and h gives us minus 19. I don't know about you, but I don't keep factors of minus 216 in my head. So to solve this, we would need to go to the quadratic function spreadsheet, and let's see, what was our a, b, and c? So we got minus 19 and a minus 216. So we got a minus 19 and a minus 216. Let me just check to make sure that's what it was. Yes, B's minus 19, C's a minus 216, and A is equal to 1. And in this case, we don't have to worry about the minus 3, because once we find our solution, we're just going to multiply everything by the minus 3. Okay, so again, let's erase this. Okay, so we're looking for factors of minus 216 such that g times h equals minus 216, and the sum of g and h is minus 19. So let's go to the create factor table. We should already have this minus 216 here. Okay, and let's start from fresh and delete these values. Now, again, we want to use the smallest number that divides evenly into 216. And we see our first two factors sum to minus 106. We want something that sums to minus 19. Okay, we use 2 again. It's not quite minus 19. Let's use 2, because 2 can go into minus 54. Aha, and here we go. Here we have 8 and minus 27. The product of 8 and minus 27 is minus 216, and when you add these two together, they give you minus 19. So if we go back to our quadratic function table tab, we put a here, if we put 8 here, hit enter, you see that does give us a solution, x plus 8 and x plus a negative 27, or x minus 27. So let's go back to our problem we were working on here, and again we said we need a g and h that such that when you add them together, they give us minus, when you multiply them together, they give us minus 216. When you add them together, they give us minus 19. And so we had solved this before, but I just wanted to show you how we got those values. So when g is equal to 8 and h is equal to minus 27, we can put those in here, and we actually do that down here. So g is equal to 8. Here we could have put g equal to 8, and h is equal to minus 27. We do that here. If you multiply those together and you add our greatest common factor, that's equal to the quadratic function that we started with. So we have a trinomial quadratic function that's multiplied times our greatest common factor, we know that's going to be equal to our greatest common factor times the two binomials, that such that when they're multiplied together they would give us this. Okay, so our final answer is y equals minus 3, our greatest common factor, x plus 8, and x minus 27. And that having that greatest common factor pulled out again allows us to solve based on the method that we've used in the past. The only thing that we have to remember to do is to make sure that we multiply this equation by our greatest common factor. So you can see below, you've got how many questions? You've got 6 questions. And I've set up each of the questions just the way I've solved your examples above. The only thing you have to do here is replace the question marks. Wherever you see a question mark, you need to replace that with some number. And basically what you do is just go up to the example, see what numbers I actually have in there, and think about what we're doing. Think about the discussion I just had with you. And as you go through here and read it, get an understanding of what we're doing, what should be in these question marks should be pretty simple. I mean, if you take time and read through each of these examples and see what numbers here. There's a question mark here. If you go to B, it says greatest common factor is equal to question mark. Here you see greatest common factor is equal to 6, because that's the number that we pull out of here, right? So hopefully that will be helpful for you, because I'm trying to give you an understanding of the language and the meaning of the factoring in the context in which it's being used. And so I'm not putting all these numbers in this language here just to be just to have a lot of verbiage. It's so that when you're doing your math, you're thinking through what you should be thinking through, and not just like punching a number in a calculator. I'm trying to give you the verbiage and the policy and the procedures and the understanding for why you're using the numbers when and where. Okay, so that's why I structure it like this. I could have just gave you this problem here and said, okay, factor this quadratic function into 2 binomials, such that when you multiply them together, they'll give you this back. So that's the procedural way, but we're trying to understand. We're not just trying to, plow through some numbers, because this understanding will help you later on when you're at your job or running your company, and you need to have an understanding about why and how. Okay? So that's the explanation, and I'm sticking with it. Okay, hope this is helpful, and look forward to seeing you soon. All right, take care.